Hi, this is Dr. Eddie Morgan at Clovis East High School, and I want to help you with your Math 1 homework. Today we're looking at worksheet 2.1b. Remember that each of the problems on the homework help is very similar to the problem on your actual homework. And in fact, if you watch the video for that problem and look at your homework, you should be able to figure out how to do your homework. In problem number 1, it says, throughout the afternoon, the temperature of an ice cube increases until it starts to melt. So we're asking, what is the independent variable and what is the dependent variable? Well, first, what are the two variables? Well, first of all, you notice it says throughout the afternoon. Well, that means time is going by, okay? Second, we have the temperature. So our other variable is temperature. So we need to decide which is determining what. Does the temperature determine how much time has gone by, or does the time determine how much temperature goes by? And if you think about that, we can't control time. So as time goes by, the temperature increases. So the independent variable here is time. And as time goes by, it has an impact upon the temperature. Now, if I want to describe this relationship, I would say, as the time goes by, the temperature of the ice cube increases. And the ice cube melts. Now, if I'm going to graph this, draw myself two lines here. We always put the independent on the bottom, so we're going to put the time here. And we're going to put the temperature here. All right. So at the beginning, as time starts at 0, we have a temperature down here at freezing. But as time goes by, it increases, and it increases slowly, and finally reaches the point where it comes to room temperature and stops. So we have the temperature depends upon time, and as time goes by, the temperature increases until it gets to room temperature, and now it's all completely melted. Problem 2 says that Grant plays a game at the Boardwalk. He pays $1 per throw until he won the giant stuffed St. Bernard. So what are my two variables here? If you look closely, it says, first of all, he's paying money. So the first thing I notice is he's paying money. So he has to have money, and each time he puts down money, he gets to make a throw. So if you think about it, my independent variable is the amount of money he spends. So each time he spends, he pays $1. And then the dependent quality is the number of throws. Notice his throws are dependent upon how much money that he spends. So how would we describe this relationship? Well, each time Grant pays $1, he makes a throw. So as the money increases, throws increase. Until he wins the prize. Okay. Now, if we're going to graph that, we always put our independent first. So we're going to put the money spent on the bottom. And our throws will be on the left side. And if I just mark them off like this for each for $1, each time he gets some money, he makes a throw. And he's just going to keep doing this until finally he wins the prize, and then he stops completely. So that would be my graph. Each money, notice it's discrete. There's just a point. There's no half throws for a $1/2. $1, one throw, $2, two throws, $3, until he finally wins the prize. Problem 3 says that Bruno begins a race. He decreases his speed midway through the race for the hairpin turn, then steadily increases his speed the remainder of the race. Two variables we notice immediately. First of all, obviously, is his speed. It talks about how he decreases his speed. He begins a race, he decreases his speed for the hairpin turn, and then increases his speed. What other thing is going on? Well, he's doing a race, and the other issue that's never mentioned, but during the race, is time. And as I mentioned, almost every time you have an independent, anytime you have time, time is the independent variable. And the reason for this is very simple. You and I can't control time. Once the race starts, that's just the time it goes. But one thing he can control as time goes along is how fast is he going to run. So that's his speed. So if you think about it, at first, he starts at 0 speed. And then increases to his running speed. As he approaches the turn, he slows down. Then, out of the turn, he speeds back up. Now, how would we graph that? Well, once again, we're going to make time, which is our dependent variable, is going to be here, and here's our speed. So notice he starts at 0, and he begins immediately to increase till he gets to the speed that he likes to run. And then we're just believing that he continues to run that speed until he reaches a point where he sees a hairpin coming, and so he slows down to a slower speed, makes the turn, and then goes back up to speed and finishes the race at that speed. Problem 4 says that Amanda works as a real estate agent. She gets $500 per month as well as 5% commission on the amount of house sales she makes. All right. So as we look at this, we're thinking about what are the variables looking at here. Well, we're looking at this $500 per month, but that's standard. She gets that no matter what happens, but she gets 5% commission on all of her house sales. So one of the things that's a variable here is her sales. All right, but her sales at the same time, this all determines how much she actually makes. What are her earnings? And as we can see then, her sales, which are in dollars, determine what her earnings are, how much she makes each month. So her sales are going to determine how much she makes in total. Now how this relation works is she receives $500 as salary. She gets that even if she doesn't make a sale. Then, every time she makes a sale, she receives 5% of the sale to her earnings. Now, how would we write this out? If I draw my graph here, and I'm going to put down here, our independent is the number of sales she gets, and that's in dollars. Our dependent is the number of earnings she makes, and that again is in dollars. And we know that even when she has 0 sales, she makes $500. So that's where our graph starts. And then every time she makes a sale, she gets like 5%. So if she made a sale here, then her graph might be here. And if she got a sale here, it would be here. I can draw a graph that looks like that shows every time the sales is based upon the amount. So when she sells $1, she gets 5%, $2, 5%, and you can draw a line. The reality is it would actually look more like this. If I put it in a different color, it actually look more like this. Then she goes nothing, then she makes a sale, then she makes a sale. You could actually argue that depends on what values the sales are, how much money she's going to make. Problem 5 says that Samantha was given a prepaid phone card. She starts with $100 on the card and is allowed to text at 50 cents per text. As we look at the variables here, the biggest variable we see is going to be the number of texts she has, because every time she uses it, it gets to be 50. It costs her 50 cents. The thing we're determining here is how much money is on her card. She starts with 100, but it starts going down. So our independent quantity is going to be the number of texts that she makes. Our dependent quantity is going to be the money or the balance on the card. Now, the way this relationship works is she starts with $100, but every time she texts, the balance decreases $0.50, probably until she uses up her card or her mom decides to put more money on the card. How would we graph that? Well, once again, when we go to do our graphing, we're going to put the independent quantity first at the bottom, and that's the number of texts. The independent determines the dependent. And our dependent is the balance on the card. Now notice in this case, the card starts at $100. So our first point is going to be up there at $100. But then every time she makes a text, it goes down 50 cents. And so you're going to get something that looks like this, because there's no 25 cents. It's going to be discrete. Every time she makes a text, 50 cents, 50 cents, 50 cents, and it's just going to go down like that until it finally runs out of money. Problem 6 states that Natalie is filling balloons with helium. She knows there's a relationship between the volume of the helium and the diameter of the balloon. And if we understand that, this one's kind of difficult to determine which determines the other. Does the diameter of the balloon determine the volume or not? But although we usually put things in terms of volume of a sphere is pi r cubed, and when we write that, we're usually saying that this is our independent variable that determines the variable. So in this case, we're going to make the diameter, which is actually 2 times the radius, as our independent variable, and the volume is going to be our dependent. The diameter is probably going to be measured in something like inches, and this would of course be inches cubed. Now, what's going to happen is, as the diameter increases, the volume will increase, we'll call it cubically. Meaning, if you increase the diameter by 3, the volume is going to create 3 cubed, which is 27 times. So if we want to graph that, again, our diameter is our independent. We're going to call it inches. Our volume, however, is inches cubed. And if it's going to start at 0, and whereas a line would look like this, where it's not a line, it's a cube, and a cube is going to increase dramatically. Like when you have 1 cubed is 1, but 2 is 8, 3 is 27. In other words, it starts and then it really takes off like that. Now ultimately you reach a place where you stop and the balloon stays there because you fill it up as much as you can without it going on. Although actually that's not entirely true, because we wouldn't want to graph that. We usually just stop there, because if it actually got diameter, it should have more. All right. Problem 7 is a little bit similar to problem 6, although it's a different amount. It says if the width, height, and height of a rectangle box remain constant, the volume is determined by the length. So we got width, we got height, then we got length. But these two, they say, are going to remain constant, so they're not varying. But the length is going to vary, and the volume. So which one is dependent upon which? Well, when they give us a formula like this, they're telling us that the volume is our dependent, because it depends on what's the length, width, and height. Since the width and the height are constant, in this case, the only thing it depends upon is the length. So as you change the length of the box, the volume is going to increase. In this case, as the length increases, so does the volume. And they increase directly. By that I mean, since the volume and the height don't change, if you double the length, the volume doubles. That's what I mean. So in this case, our independent quantity is our length, and our dependent quantity is our volume. And as I said, at 0, there's 0 volume. But when I move up 2, this one moves up 2. If I move up 4, this one moves up 4. And you see that what you really have is going to be a straight line, a 45-degree angle coming out that way. All right, I hope you had an easy time with your homework tonight. Have a good day.